So in the last lecture we talked about the process of matching images. So we had an image or template of an image which looks kind of similar to a second image or database image, and the goal was to actually find a matching between our template and our reference image. And we discussed different ways on how we can achieve that. We started with the cross correlation and looked into least squares matching. And what I want to do today is, based on the findings that we kind of derived for the least squares matching, actually describing an operator that allows us to extract such point features in images. And these are a special type of point features. These are point features which I can actually localize well among images. So the goal is, we have an input image. We want to extract interest points or feature points. These are those which I then can use for establishing correspondencies with points from another image taken from the same scene. And one of the kind of goals of those images is that these features is that these are feature points which I can actually localize well in my image. So I can very precisely estimate the location of those feature points. As we motivated already a few times, those point features are kind of relevant for a lot of tasks. For example, this was an example you've seen before. These are two aerial images taken from slightly different locations, but picturing the same scene. And then we have a couple of those points. These are these black and white dots over here. And the goal is, based on those points, find the correspondencies between two images. So to which point in this image does this point, for example, belong to? And if we have those correspondencies, we can use this for 3D reconstruction. And the more accurately we know the location of those points, the better the 3D reconstruction will be. And therefore, we are interested in being able to very precisely localize those distinct points. And the goal of today is to present you a technique which allows us to find those points, and especially those points which I can localize very well. But first we have to think, what are desired properties of those point or point features? In order to find them again in another image, which may look slightly different, but still picturing the same scene, the first thing is we want to make sure we actually find the same points again. And in order to ensure that we find the same points again, or in order to have a high likelihood that we find those 2 points again, we need to have points which are distinct with respect to their local environment or neighborhood. So something which kind of sticks out, something which is special within a local region. And if we have a measure, for example, about what is special, then we have a high chance of finding those points, the same object to which this point, for example, corresponds to in both images. The other thing we are interested in, that those points can actually be detected robustly. That means even if we have slight changes in the viewpoint, even if we have slight changes in the illumination, for example, we still want to be able to find the same points. So if you go back to this original image, you can see, for example, that this image is slightly darker than the other image, than the one on the left, but we still want to be able to actually find those corresponding points. As I said also before, very important, we want to allow a precise localization of those points. So we want to be able to as accurately as possible find the correct location of those interest points. So if we find them in those images, we can locate them very precisely, and we have a very small uncertainty about where they actually are in those images. Because the more accurately we know the corresponding points, the more accurately we can localize them, the better our 3D reconstruction, so our estimation of the depth, will be later on. Maybe we are also interested in image interpretation, so do those points actually tell us something about the image, or can we actually use this in order to, for example, do some semantic interpretation? That's something we actually start with next week with classification task. Although, so this point is currently not that relevant for the point feature that I'm presenting here today, but we also may be interested in having features, for example, edges, which have some semantic interpretation. But this is kind of a wish list for those point features. This is something which is not explicitly addressed here today, at least. So what we want to look today into is, how can we actually find those distinct points, and especially want to look to those distinct points or feature points that I can actually localize well in my images. So this is our task today, and we built what I'm going to present here based on the least squares matching chapter. So the idea of performing this least square matching is something which we'll now build upon in order to actually localize those points. So the key goal is to identify distinct points or regions that can be localized well and that we then can use for finding correspondencies. So with these two images, or these are also a stereo pair of images, given all those points over here, and if we can localize them precisely, then we can actually do a good 3D reconstruction. And we'll now focus into the ability to localize those points. Okay, if we go back to the least squares matching approach, and we only look into translation for the moment. So we only have a translation in X and in our Y direction. And the result of the least squares matching chapter was that we end up having a system of linear equations which looks like this. So this is a 2x2 matrix. There's a 2 vector and another 2 vector. And what the elements of this normal equation actually turns out to be is these are all sums about m pixels, so kind of a local neighborhood about the pixel we're investigating. So the pixel I and j and I, or I and j, are those pixels we're looking into. And these f here are the first derivatives with respect to I or with respect to j. And these m is kind of the points in the local neighborhood of that shift. So we have a shift over here. We're kind of inspecting the neighborhood of those points. And what these elements here actually are, these are the gradients or the first derivatives of our intensity function, our image function, with respect to the x and y or I and j dimension. And so we have here the squared gradients, the gradient in x direction and the gradient squared in y direction, and here the product of the gradient in x and in y. So the matrix n over here, only depends on on the gradients. The gradients computed at a certain location, and then we have the sum over these m pixels which are involved in the local neighborhood. And we have the shift. Then we have here again the first derivative and the difference in the intensity values. But the key thing we want to look into is this matrix n over here. Because this is the system of linear equations that we actually have to solve if we want to estimate the shift of two image regions with respect to each other. And this was a result of the image matching chapter last week. What we also looked into, we said, okay, the uncertainty that is related to this shift is related to exactly this matrix, and actually the inverse of this matrix, times another factor, which in this case is the variance that we have in terms of the noise in our intensity function, our image function, so which represents the image intensities. So what this means is the larger those values are in here, the less accurate I actually can determine the shift. And this is inverse proportional or related, so it's inverse proportional to this matrix n. And this is the sum of the gradients. So the larger the gradients are, the better we can localize our points. So what we look at actually, how steep are the gradients in our image function, and we simply sum over the gradients in a local region. And the larger those values are, the smaller the elements of the covariance matrix for the shift will be. So this is kind of this important relationship that we have in here. This is also something we have seen last week. So kind of to sum this up, this was our system of linear equations. This is our matrix n. And what we can actually do, we can write this matrix n here as the average squared gradients times a factor m. So m is where the pixels involved in the local neighborhood in which I do my computations. And so my matrix n is simply the average gradient computed over m pixels times m. Because we basically sum over m pixels and sum up all the gradients. I can also say this is simply the average times m. So this is exactly the same result as this result over here. So I can write this in this form. Let's say if these are simply sums, then I can simply write those sums as using a box filter, and simply the size of this box filter tells me about how many elements I'm actually summing, because the box filter was not doing anything else than just summing over the individual values divided by m. So I can simply rewrite my matrix n in this form over here. So just have the individual values of the gradient convolved with a box filter. And this basically computes the average squared gradient, or so for this, the average squared gradient of this region. And so I can actually rewrite n, this matrix n, of exactly having this form. It's also something we have seen in the least squares matching chapter last week. And if we assume that those gradients over here have a zero mean, and if you take into account how we computed those basically using the Wrobl operator, if we move over image, then if you remember that the sum of the elements of the Wrobl operator or the gradient operator was 0, so we are expected to obtain a zero mean, and basically have exactly these zero means, then this corresponds to the uncertainty, to the covariance matrix of the gradients. So we look into the covariance matrix of the gradients, and I can express my matrix n as simply m times the number of pixels involved times the covariance matrix of those gradients. So this is basically what I have basically here is the variance in the gradients. So the variance in 1D or the covariance in multiple dimensions. And I can now use this matrix, the covariance matrix of the gradients, and can relate the covariance matrix of the gradients with the covariance matrix of the shift. Right? We said the covariance matrix of the shift is the variance of the noise times n inverse. So I can now put actually this element in there. So this just copy paste from the previous slide. Say, okay, the covariance of the shift, we said before, is the variance of the noise and the intensity function times n inverse. So take this n, replaces by these elements over here. So this goes in here, and the m goes down here, because it's 1 divided by m. And then I can replace this by the covariance matrix of the gradients. So what we now have is a relationship that the uncertainty in the position of those points is inverse proportional to the uncertainty of the gradients. There's a variance in the gradients, the variance in the gradients. So it should be variance. Okay, so we have this direct relationship, which tells me in this equation, the larger the variance that corresponds to the noise, the larger the uncertainty in my shift. This also intuitively makes sense. So if I have a more noisy signal, a more noisy image function, it will be more difficult to actually localize those points well. Okay? The second thing we have is that there's a relation with m. So the larger the number of images, of pixels I'm investigating is, so kind of my local window that I'm looking into, the larger this value is, the smaller the uncertainty about the shift is. Basically means the more pixels I take into account, the more precisely I can actually localize my local patch. Kind of also makes sense. If you have a very, very small patch, you will see smaller, you just have maybe one gradient in there, but if you have a larger image region where you see more gradients, you will be able to localize yourself more accurately. And the third element it actually depends on is this part over here, is the average squared gradients. So I compute the first derivative, compute the squares, and the larger those values are, the better I can localize myself. Okay? So it's kind of, is this concept clear because it's central for this feature detector? So the larger the gradients are, the better I can localize my points. It's kind of the key take-home message from this first part over here. It was something which was a direct result of the matching chapter discussed last time. Okay, any questions so far? Okay, so if we now look, so we have a 2D problem, and if we now look into the shape of the covariance matrices involved for the shift, we basically see 3 different possibilities what we can experience. The first thing is we have very small and potentially circular ellipses, let's say, corresponding to the 1 or 2 sigma bounds. So something like this means a small circle means I can actually localize my points quite well. What can also happen that along one dimension we have a high uncertainty, but along a second dimension we can actually localize ourselves better. So to which kind of local structure does something like this correspond to? Okay.
One large uniform color object in the image.
Is this one large uniform color object in an image?
No, but for example, an edge in the image.
Yeah.
2-color image, 1 stripe.
Exactly. So it could be a perfect, let's say, a black and a white area. That means they are very well localized in the direction of the gradient, where the gradient is steep, because we see the edge, but we can kind of slide the black and the white areas among each other and don't get any different values. So we have a high uncertainty where we are along this edge. In this example over here, that we have a high uncertainty in all directions. This is exactly the case you mentioned before. This is just a more or less uniformly colored area. So they're kind of 3 different things. The first thing is, as I said, what we typically have, which is an irregular texture, so a texture with a distinct pattern, for example, where we can localize us very well in both dimensions, so in the x within the y direction. Then we obtain something like this. Or we have the second situation that we have one eigenvalue of this covariance matrix is large. This represents or corresponds to the, well, that means that in the direction of the eigenvector corresponding to this eigenvalue, we have a high uncertainty. Or the third case, which is basically a homogeneously colored area, which is not well suited to find localized points because all areas have basically more or less the same intensity value, so the same color. And that means we have 2 large eigenvalues over here. Also have an illustration how that could look like. So for example, we have a white area here and a grayish area over here. There's some kind of small spots in there. This is just due to the noise that we have. So if we have this kind of shape, where we have steep gradients in this direction and steep gradients in this direction over here, that means so if we have a second image we could slide on top and illustrate the differences, is that we will see a lot of differences if we move it within the x or with respect to the y direction. This does not matter because we have an edge in the vertical as well as in the horizontal direction. So this is an image region which I can localize very well with respect to the shift. So there's a very small ambiguity with respect to the shift if I see an area like this. If I see an area like this one over here, we have only the gradient in one direction, then I'm very well localized in this direction, but I'm quite badly localized in this direction. So if I would have a second image, I could slide the image in this direction and I would see no differences in the images. So that means I cannot localize in this direction, I can only localize in the horizontal direction. And if I have a uniformly colored area, maybe with some noise in the intensity values, then we are very uncertain. So I can basically move this gray area in every direction. I will more or less get the same matching. So this is bad for us. This is maybe good, maybe not good, maybe good only in one direction. And this is something which is good. So what we in the end want to do is we want to find areas which look like this. If we find areas like this, that means at least we have points which are localized very well. Okay, so go back and remember what our goals were. The goals were we want to find image regions or points, if you consider their local neighborhood, that these are points where the uncertainty with respect to the shift is small. That means that the eigenvalues of this covariance matrix are small. So both should be small. And we want to have points which are kind of better than their neighbors. So one of these distinct points that we want to find. This is our goal. This is what I want to do now. I want to find those points for which these two properties hold. Of course, just to mention this is not really a point that we are considering here because we are summing over local neighborhood. So we can see this as we're taking into account the local pixel neighborhood of this point in order to evaluate can we localize this point well, or if this is a distinct point, so it's better than its neighbors. Okay, any questions up to this point? Anything which was unclear so far? Is there anything I can explain? Yeah, bitte.
So, the bigger the gradient, the more difference we have if we switch the two images.
Yeah, so the question was, just repeat it here for the recordings, the larger the squared gradients are, the smaller the elements of this covariance matrix will be. And this means that if we would take kind of the same images and overlay them, let's say we have, maybe just illustrate that again. We have one image over here, and this is kind of all dark, and this is a bright area. And now we have a second region, which also looks like this. So dark and bright area. But I can actually take this one and slide it along this dimension, and it will perfectly match. The reason is because in this direction we don't have any gradient. What we have, we only have gradients in this direction. So we have, this is where we have a strong gradient, and therefore we can actually localize it very well in the horizontal direction, but we cannot localize this well in the vertical direction. So this would give us an uncertainty ellipse, which would look like this. So we would have one eigenvector which corresponds to a large eigenvalue. So eigenvalue is large. But in this direction, lambda is small. So did this answer the question? Okay. Any further questions? Okay, what we can now do based on this, we can now simply write down an algorithm on how we actually extract those distinct points. Okay, so the first thing we do is we compute the covariance matrix of the gradients. What this involves is computing those elements over here, which first involves computing the gradients. So for every pixel location, we need to compute the gradient in the x direction as well as in the y direction. Is there anything I can help you with? Guys, anything I can help you with?
No.
Okay. So what we need to do is we need to compute the first derivative with respect to x and the first derivative with respect to y for every pixel location. And then I need to compute this covariance matrix. The first thing, or this is the important thing which I need to do. So the question is now, how many computations are involved in that? So what kind of computations do we need to execute in order to compute those values over here? So what are the operations that we need to do? How do we compute the gradients? We have an image function. How do we compute the gradient of this image function? Yeah? Exactly. We use the Wrobl operator. So this means we have a convolution with the Wrobl for the x direction and a convolution with the Wrobl for the y direction. So we need to compute two convolutions in order to get this fjm and fim. What else do we need to do for every pixel? We need to square those values. So the gradient in x times the gradient in x, the gradient in y times the gradient in y, the gradient in x times the gradient in y. So we have 3 multiplications which are involved for every pixel. What else? So far what we now have is we have those values computed, this one, and this one over there. What else do we need to do? Yeah? In the end, we need to divide by m. So in the end, we have 4 values that we need to divide by m. This is true. What else? We sum it up. How do we do the sum? How can we compute the sum?
Well, with the squares, you just multiply the transfer and the vector with its what is it, transform, and you automatically get the sum of the squares.
Okay, we could do that for every point, but how we do this in practice is we basically use a convolution. So we again use simply the box operator and have another convolution. So we need to have 1, 2, and 3 convolutions because those 2 elements are the same. So we have 2 convolutions for the gradients, 3 convolutions for the sums, and we need to compute for computing the squares, we need to have 3 multiplications, and we of course need to divide by m, which are again 4 multiplications. Okay, this is what this ends up to be, and we need to do this for every element in there. Okay, so this is done. Now we have all those values computed. What's the next step that we need to do? So we now have our gradients. We assume the noise in the image function is everywhere the same, and we have the same sized window we slide over our image. So m is always constant for the whole operation. So the remaining thing we need to take into account is computing the eigenvalues. We're especially interested into looking into the smallest eigenvalue. We know we have 2 eigenvalues because we have a 2D covariance matrix, and we are interested in the smallest eigenvalue. So also something you know how to do that. So the smallest eigenvalue has exactly this shape. If these corresponds to the individual elements of our matrix. So we would have actually a plus minus here from the equations, but it's clear that the plus will be the larger eigenvalue, so we are taking into account the smaller eigenvalue here. So we're using this operation where we basically need to compute a few sums, multiply a few values, and need to compute a square root. We actually obtain the smallest eigenvalue of my gradients. Why am I interested in the smallest eigenvalue of the gradients? Yeah. No, I mean, we just have 2. We just have the smaller and the larger one because we have a 2D problem. So I guess that was not the answer that I was expecting, at least. So this has, at the moment, this has nothing to do with distinctiveness. The question is, why do we take the smaller one and not the larger one over here? I should formulate this question better. So why are we interested here in finding the smallest eigenvector of the gradients and not the larger eigenvector of the gradients? So what does the smallest eigenvector of the covariance matrix of the gradients tell me? Not of the shift, of the gradients. Yeah.
I'm looking for the smallest eigenvectors because I'm looking for the minimum of the squares. And the smallest eigenvector gives me a small circle, gives me a high certainty.
So this is the point. The smallest eigenvector in the gradients will give me the largest eigenvalue in the shift. What I'm doing here is basically, if I compute the smallest eigenvalue of the gradient, this corresponds to the largest eigenvalue of the shift, and I can simply just check the largest eigenvalue with respect to the shift, and then simply let's use a threshold there. I want to have that the dimension of largest uncertainty should be smaller than, for example, 0.1 pixel or 0.5 pixels. So I compute the smallest eigenvalue of the covariance matrix of the gradients because this gives me an upper bound on the uncertainty of the shift. So this is the eigenvector corresponding to this eigenvalue is the dimension along which I can localize the worst. And I want to kind of have a bound on the worst possible localization of my points. Okay? This is because the largest eigenvalue and the smallest eigenvalue, as one matrix is the other one inverted, is just given by 1 divided by the other eigenvalue. So the maximum eigenvalue with respect to the uncertainty of the shift is given by a constant, and then 1 divided by the smallest eigenvalue of my gradients. And then I can simply say, okay, this value here tells me what is the uncertainty that I have along the dimension along which I can localize worst. What I then can do is I say, okay, I simply want to have this value being smaller than, for example, a certain threshold. So I can say, okay, this should be smaller than a threshold. For example, my threshold can be 0.5 pixels. That means, in this case, the standard deviation for the shift should be smaller than, let's say, 0.5 pixels. That means I will only find points which can be localized better than 0.5 pixel in terms of their standard deviation. Everything else I'll throw away. I'm not interested in the rest, because all the points of which this does not hold are simply points which I cannot localize well. So what we do is, we now find all those points. We can label all those pixels for which this holds. We've labeled all the pixels which I can localize well. And then we have the second condition we want to take into account. The second condition which we want to have points which are better than all their neighbors. Right? We want to have kind of these locally distinct points. So what we can do is, we can simply slide over our image. We have, for large regions of the image, we won't have any value because they do not, this condition does not hold. But if this condition holds, we may actually have multiple pixels in a local area for which this condition holds. And then we want to take the point which has the smallest, largest eigenvalue. So inspect all the largest eigenvalues and select the one which is the smallest one. What we do for that is we slide over our image with a local window and simply look into this local window and say, which is the smallest point in this local window? So for example, we have here, let's say, this is a region we are interested in over here. We can kind of slide this black rectangle over this region and simply look into how many points, or what is the smallest, largest eigenvalue in this rectangle. And I kind of find the rectangle, so this value is the smallest. That means the points I can best localize best. So you have 3 different possibilities here. Which is likely to be the point for which this condition holds? So which of those areas I'm likely to localize best? So we assume they all have the same variance, which corresponds to the noise in my intensity values, and they all have the same size, so the same number of pixels. So if this one a good interest point? This one or this one? So 1, 2, 3. Who's for 1? Who thinks 1 is a good idea? Who thinks 2 is a good idea? Who thinks 3 is a good idea? Okay, so the majority 1. This is a good idea. Why is this a good idea? Because the points in here, if you look over this region, there's the largest number of gradients in x and in y direction, which then allows me to localize well. So this point simply happens in here I don't have any gradients, and in here I don't have any gradients. So it's getting better over here. Of course, if I go too close to one boundary, I'm completely losing one dimension, and then kind of the largest eigenvalue gets much, much larger. Therefore, I still need to make sure I see enough of the white region, but still have enough gradients over here. So, but this is the one which we would pick, and this is something which is known as the Förstner operator, which Wolfgang developed in, I'm not sure, something around the beginning of the 80s, I think. And this was one of the operators which was explicitly targeted to be localized well, to be able to be precisely localized. So if I do 3D reconstruction, I get a very good estimate of those points, so that I then, as a result, get a good estimate of the depth information to get 3D information. So kind of to sum that up with a small picture, we start with our image function f. We have our two Wrobl operators, one in the x and one in the y dimension. So I convolve f with the Wrobl operator and get my gx and gy. These are the kind of the two convolutions that I need to conduct. So for every pixel, I get kind of two values now. The gradient in x and the gradient in y. Then I need to square these guys, and compute gx times gy. So I have 3 multiplications. So carry out the multiplications, and then obtain gx squared, gx gy squared. So 3 multiplications, what I executed. What I then need to do, I need to compute the sum over those values over here. And as you said before, we do this by convolutions with the box operator. So we add 3 convolutions with the box operator, and this then gives me the average squared gradient, which I directly obtain those elements of the matrix, of the covariance matrix of the gradients, which I then need to do in order to compute all the eigenvalues. Then I analyze the largest eigenvalues with respect to the shift. So I get the maximum, and then I do a thresholding, simply tell is this larger or smaller. And then I get the output. Input is the image function, and the output are those points which are kind of distinct. I mean, they're smaller than that, of course, and they need to be locally distinct. So I have an example. For example, if I have here the squared shown in different directions, we can actually see that those interest points are actually computed along the corners, and these are exactly those points which I can localize well. So along those edges, I cannot localize very well, because I can kind of slide along these edges, but at the corners, I'm actually able to localize well. And all the examples that you have seen so far in the lecture are actually those points coming from the Förstner operator. So those points which I can localize well. So I told you now that these are points which I can exploit for stereo reconstruction, or for estimating depth, for example, from stereo images, from 2 images. So I want to have a very quick look into how that works for a simplified case, which is the stereo normal case. So remember the stereo normal case. We have 2 images. The images are shifted with respect to x. So along the x dimension, just 2 images were taken, either from the same camera, just the camera shifted, or from 2 cameras. And what we also looked into in the chapter on least square matching was we could see that the only thing which matters with respect to the depth information is the parallax in y. That was the difference in the x pixels in the left and the right image. And given this special setup that the camera is only shifted in x and both look into the same direction, The y location, the y pixels in both images for corresponding points should be 0. So there's a 0 y parallax, at least in the perfect case, if the cameras are mounted perfectly. So the only thing we need to take into account is the parallax in x. So it means how accurately can we actually localize a point only in the x direction. In this setup, we can ignore the y direction. This only holds for the stereo normal case where the cameras are set up in this special way. And if I would set up the cameras differently, I would need to take into account how accurately can I localize this point in x and in y. But in the stereo normal case, this is the x dimension is the one which matters. So this leads to the fact that the search for correspondences is basically a 1D search problem. So for this point over here, I know that the corresponding point must lie along this line, so I only have to search along this line in the second image. Because I know the y coordinate must be the same for corresponding points. So in this case, if I want to use the first operator for this operation, I only need to check how well can I localize with respect to the x dimension. So it's a simpler problem. So we can take our 2D problem that we have in here, just copy paste from the first slide of the course today, and I'll say, okay, we are only interested in one dimension, in the dimension in x. So we just need to take this 2D problem, reduces to a 1D problem. I just have the gradient in x, squared gradient in x, the average one. This is a shift in x, and the other side of my system of normal equations, so it's just kind of one equation which is left. But anyway, exactly the same what we have done before applies. So we can compute the uncertainty with respect to the shift, which basically depends the larger the noise in the image, the larger the uncertainty in the localization. The more pixels we have, the smaller the uncertainty, and the larger the variance of the gradients, the smaller the positional uncertainty with respect to the shift. So it's exactly the same on what we have done before, but just looking into a 1D problem, so just to shift in x. So we just need to look into the shift in x and basically look to the position where the squared gradient in the x direction is maximized. And these are those points which I should use for my stereo reconstruction. So it's a simpler problem because it's just a 1D problem. What one does in practice, one basically, if this is kind of the line where I expect the pixel to be, I typically take into account also one plus minus one line, so to avoid kind of missing one. But this is just, I just slide this block in this direction and look for the point which have a very distinct gradient. I do that in both images and take those as points for my correspondences, because these are the points which I can localize well, and then I can expect that for these points I get an high quality depth information, so an accurate depth estimate, which allows me to compute the location of the point in the three-dimensional space. Okay, to sum that up a little bit, what we've done, we looked into distinct points, say what makes a point better than its neighbors or other points in my image. We looked into this question from the special, under the special question on what are points which I can localize well, because this allows me to do good 3D reconstruction. So what we want to do is we want to come up with a point operator that allows me to do good data association and localize those points very well in order to allow for an accurate 3D reconstruction. And we were exploiting the least squares technique that we introduced in the last lecture. And then looked which are those points which under these least square estimate can be localized well. So where the eigenvalues of the covariance matrix of the shift are small. I simply have thrown away all points where the largest eigenvalue of the covariance matrix of the shift was larger than the certain threshold, and then looking in the local neighborhood for the point which performs best. And these are my distinct points. And just an example of what one can do with that in a stereo setup. So what you see here are two stereo pairs mounted on a helicopter, on a quadcopter, or octocopter actually to be precise. These are two images looking to the front, but these are two images looking to the back. And you see a couple of points in here. These are not exactly the points which I have presented here, but kind of points related to that. And what we can do now is while the copter is flying, we get, let's say, 10 times per second a new image. We can look for those corresponding points, triangulate those corresponding points. So given that I know how far the camera is away, and I know the correspondences between points, I can actually estimate where the point in the 3D world. I can actually estimate the location of those points, and as a result of that, also the location of the cameras moving through the world. And this is how it typically looks. Something like this typically looks like. You see here the platform flying at Frankenforst, here on the other side of the Rhine. And you see new points popping up because the copter flies into new regions, and there are new points showing up of areas I haven't seen before, which I can use for the 3D reconstruction. And I'm doing this with the camera looking to the front and the camera looking to the back. And based on those corresponding points, and a technique which is called bundle adjustment, which we will introduce in the second part of the photogrammetry course, so this fall, we can actually precisely with the least squares approach estimate where those points are in the space and where actually also the cameras are or have been when we're taking those images. And as a result of that, I can kind of build a map of those distinct points, know where they are in space, and I can also estimate where my platform or my helicopter is in space. That's it from my side about point features. We'll go back and look into point features again in Photogrammetry II, looking into other popular type of point operators. But for everything we do within the next half year, these are points or point features that we can use to do our operations. So we from now on assume those points to be given. We assume to have corresponding points. And this is a technique on how to obtain those points, and then just matching those points between those images, for example, with this stereo matching principle, doing this for the stereo normal case. We also relax that in Photogrammetry II from the stereo normal case to the general case, how cameras can be oriented. But so far, we kind of say, okay, we have this stereo normal case. Are there any questions about this procedure? So the key take-home message is, there are distinct points, we can compute them in our image. So if someone talks about corresponding points, this is a technique to look up and to use. And those points have this nice property that they can actually be localized very well, which is the objective of a lot of point operators, but was here the clear objective from this approach, and actually using the squares approach in order to derive which are those points which perform best. Okay? There are no further questions? Just make a 5-minute break, and then I'm going to continue. Thank you.